morning everyone. The topic is divide and conquer. And in the divide and conquer, we will cover the first application of divide and conquer, that is quick short. So my name is Vishal Chaudhary, Assistant Professor, Department of CSC, AKGEC, Ghaziabad. So first I'll cover the quick short, then algorithm performance and conclusion part of quick short. Now see, so as I told you, it is the application divide and conquer. So it follows the divide and conquer paradigm. It's the first design technique of algorithms, divide and conquer. So it's the first application divide and conquer. Now, the first word divide. Actually, in this quick sort, we have to sort the array in a sorting form, like in the ascending order, descending order. So in the first part divide, we will partitioning the array into two parts. Basically, it not just divide the array into two parts, it basically divide the array into two parts in a meaningful way. That means we select the pivot, all the element before the pivot should be below or the less than the pivot, or the element larger than pivot should be the next in the next half of the array. The first part, partitioning, separate the array APR into two possible non-empty subarrays. That means we have taken the either first value or last value as a pivot, and we will place after the first partition pivot at its correct position. That is AP Q minus 1 and AQ plus 1 R. Next, each element in AP up to Q minus 1 less than AQ, where Q is the middle element, right? And the AQ greater than equals to each element in the next subarray should be larger than the AQ. AQ is basically here is the pivot element, whereas the index Q is computed as a part of the partitioning procedure. Now, next part, conquer. Now, sort the two subarrays A, P, Q minus 1 and AQ plus 1 R by recursively calls quick sort. Now, we will recursively call the quick sort recursively up till we get the smallest element as single element. Now, combine. Since the subarrays are sorted in place, no work is needed to combine them. It's an in place algorithm, so we don't need to any work to combine them. Now, this is the algorithm of quick sort. See this part. In this quick sort, there is an array A with a two index array P and R. P is the starting index, R is the pivot element. Suppose here in this algorithm, we have taken last element of the array as a pivot element if P less than R. That means we are checking the condition if we have an array element in the array or not. See, if less than P equals to R, then Q, partitioning A, P, R. A is the array, P is the first element, R is the last element, which is our pivot also. Now, we will recursively call the quick sort on two subarrays. Like the first part is this A, P, Q minus 1, and second part is middle element Q, then AQ plus 1 R. Next. Now, this is the hero, partitioning. Now, we will recursively call an algorithm or a function call which is partitioning here, that is, which will partition the algorithm, divide the algorithm two parts on the basis of the pivot element. Now, partitioning algorithm, partitioning APR, see, APR x equals to AR. Now, first what we will do, we will store the pivot element in the variable x. And here in this algorithm, I have taken the last value, which is 5 here as a pivot. See, now I equals to P minus 1. The first index is P, and we have taken the I value equals to P minus, that is index 0. If I have started the index with 1. Now for J, P to R minus 1, we will start a loop. What it is saying, if I have taken this array, this is 1, 2, positions of the array, 3, 4, 5, 6. So here, x equals to value of this array. Suppose this is an A array, A, R, the last value. Here, suppose it is a 5, suppose. Now we have two pointers. Here it is P, which is already equal to J, and I equals to P minus 1. That is I somewhere here, somewhere 0 out of the array. Now see, now we will see a loop from J, P to R minus 1. That means loop will run from this position from 1 to this, because this is the R value, R position, to R minus 1. Here, do. Now we will check what? We will check the value of aj, j starting from p here, aj with the value of pivot. This is pivot. So the p to r minus 1, if j, now we will check the value of j from the starting index with the pivot value. If it is less than equals to then we will increment the I here is starting at the index at 0. So see, let's see with the example. Now here is a partitioning algorithm. Same values are last value is a pivot into x and I equals to p minus 1. Now from j, p to r minus 1, see this part. We have a input array value 2, 5, 8, 3, 9, 4, 1, 7, 10, 6. Now the pivot is last value which is r here 6. Now after this first partitioning, the pivot will lead to its exact position somewhere here or here. Let's see. Now the j is the starting index, I before the starting index it is 0. Now we will check the condition. If aj less than x, x value 6 less than x, here 2 less than 6, true. We will initialize the I which is incremented by 1. Now see, I is here. Now again j is here. Now second loop, we will check the again j value with the pivot x is 6. Now this value, first we will check this value. Now 5, 6, it is smaller. Again I is incremented. Now third value, third is this, j is here. Now j is here, we will check the value, either this j less than pivot, no, this time no. So we will not into this if condition, or I is not incremented here. Now see, no incrementation. Now what it will do, it will swap the values with the incremented value of j, this. If this not, then this. Now I, it was here, now incremented with this here and this and swap. Next. Now I is here, j is here. Now again I is incremented here. We will check this value, I is incremented. Now next value, we will check this value, this less, again I incremented. Now j is somewhere here. Now again I is here, j reaches to I value, will stop here because j reaches to r. Now we will check this condition. Now we will swap these values. This, see, I is somewhere here and swap this. It is, see, 6 came to here, 6, now 8. Now let's see the analysis part. Now all the values lesser than 6 is less before the 6 value. This is our pivot. So the array is divided into two parts in a meaningful way. All the values smaller than pivot is less than here, and all the values greater than pivot is the right side of the array. See, 9, 7, 10, 8. Lesser values 2, 5, 3, 4, 1. Now see, select the last element AR in the subarray as a pivot. I have selected the AR. AR is the last value in the array. This AR, last value. Now, as the procedure executes, the array is partitioned somewhere into 4 or 3 possible ways. Basically, 3 possible ways. Which one are? This, see. Somewhere here are this partitioning to three possible ways, or 3 partitioning. 1 partitioning, second the pivot itself, and the third partitioning. Now, see, when the loop terminates, when j equals to r, so all the elements in the A are partitioned into one of the 3 cases. Either the pivot value, the left subarray is less than the A p up to I, which is less than the pivot, first partitioning. Second partitioning, A I plus 1 up to j minus 1 greater than pivot. It is talking about this is pivot, this part. And the first case, this is talking about this part. If this is the pivot, P. Now the third case is the middle one, pivot value. when AR equals to pivot. So these are the three cases or the three division of the array. Now, the last two line swaps AI plus 1 and AR, pivot moves from the end to the array between the two sub-arrays. That means at the last of the algorithm, we will place the pivot element at its correct position. Somewhere. Maybe it could be this, it could be this, or it could be this. That depends. So this is the procedure partitioning correctly performs the divide step. Now we will analyze the time complexity of this algorithm. See, running time of quick sort depends on whether the partitioning is balanced or not. That means we are dividing the array into two parts. Now, if we suppose the last element is 1, which we have selected as a pivot, if it's the correct position is here 1, then always the partitioning is like this. Suppose next sub array, it is 2, again partitioning is like this, all with the right sub gap. It is not a balanced tree, right? It is not a balanced. That's why it is a worst case partitioning. We are not balancing the tree. Always some gaps are there. This is the worst case partitioning or the unbalanced partitions. Now, it occurs when every call to partitioning results in the most unbalanced partitioning. It could be happen. Partitioning is most unbalanced when the problem 1 is of size n-1. That means we are dividing the problem into two parts on the basis of partitioning, and the one side is 0 partitioning and the other side is exactly n-1 array problem size here, and the problem 2 is of size 0, it is 0 size, or vice versa. Maybe this could be the case, always 0 and n-1, again n-2, 0 partitioning, either the left gap or the right gap. So these both are the cases of worst case partitioning. Now, pivot greater than every element in this, or a pivot less than every element in this. These are the cases. Every call to partitioning is most unbalanced when somewhere array sorted or reverse sorted. Suppose it means when this case will happen, when the worst case will happen, when the array is already sorted. Suppose 50, 40, 20, 10. And we have taken the last element as a pivot, this. So after the first partitioning, what will happen? 10 will come here and this rest of the array. Suppose it is 20 now, or again 20 rest of the array. Here the array is always sorted in the descending order and we have taken the last element as a pivot. So this is the case of worst case partitioning. See, recursion tree is like this. n-1, one side is 0. Again, one side is 0. n-2, one side is 0. n-3, one side is 0. Means the size of the subproblem is divided into two parts, 0 and n-1 size. Again, 0 and n-2 size. 0 and n-3 size. 0 and n-2. Same, 2, 1. We'll stop here. So the running time for the worst case partitioning each recursive level equals to t n-1. How this is possible? See, it is n-1, it is n. Again, 0, 0, n-2. So the partitioning will take n time. And this again, t n-1. See, tn equals to total time. This is 0 plus this t n-1 plus this partitioning time. So this is close to 0, constant. See this part, t n-1 plus n. So now here the recursion tree. See, we have close to n-1 levels because every level is n-1, n-2, n-3 up to 1, and cost of each level is n. So n-1 levels into n. It is n square. The bigger function is n square. So the worst case time complexity is n square. Now the best case, when it will happen? It will happen when we divide the array into two equal parts. Again, two equal parts. When it will happen, suppose we have an array like this, 2, 3, 6, 8, 5. Now the last element we have taken as an pivot. So after the first partition, it will reach to where? Exactly this. Now 5, it is 2, 3, it is 6, 8. So it is the equal partitioning. Next equal. So we are dividing the problem into two equal parts. We got a balanced tree. So this is the case. So the size of each subproblem less than equals to n by 2. One of the subproblem is of size n by 2, other of size n by 2 minus 1 close to this. The recurrence for the running time. Now see, reconciliation देखते हैं इसका. See, this is n. It is n by 2. It is n by 2. Now it is not 0 here. It is not n minus 1. It is exactly n by 2, n by 2. And the dividing time is n. Dividing time is n. Now the reconciliation is Tn equals to two recursive calls. 1, 1. So equals to 2 T n by 2 plus divide time n. Partitioning time n. So it is n log n. So it is n log n. So we have seen the worst case partitioning, which is what it is. In this case, we have got the complexity n square. In the best case, it is n log n. Now, is the recursion tree for the best case partitioning. When we have divide the array into two parts, two equal size. See this. Now, when we are dividing the array or the problem into two equal parts, the size of the tree, or the height of the tree is what? Log n. Always equal, always equal, always equal, and the cost of each division is n. So total cost कितनी आ गई हमारी? Total cost is n log n, and we have seen here also n log n. So this is the best case partitioning. Now this is the recursion tree for best case. Now see the average case. What will happen in the average case? In the average case complexity, it is close to sometimes equal, sometimes gap, sometimes equal, sometimes gap, sometimes equal, sometimes gap. So what will happen in this case? In the average case, the array is lucky when we have got the equal division, and union unlucky when one side gap. So suppose करिए for the reconciliation 2t n by 2 plus n, when we get the exact partitioning. Now second time there is a one side gap, so it is 2t n by 2 minus 1 plus n minus 1 plus 1. Suppose करिए, so it is close to 2t n by 2 plus 1. How? Some constants only. So the average case of this quick short is close to best case. So the average case complexity is also n log n. So now conclude this part. So the time complexity Tc for the best case, it is n log n. For the average case, it is n log n. For the worst case, what it is? It is big of n square. Now, the conclusion part. So the divide and conquer is just one of the several powerful techniques for algorithm designing. In the divide and conquer, we have seen the complexities and the algorithm part of the quick shot. So can lead to the most efficient algorithm. So that's it.